Good morning. Thank you for getting me to this nice place. And I will try to cover some things which is, I mean, there have been a lot of talks that speak about sources that can be detected in this year's regime, and I will try to have a somewhat biased view from my side. Okay. So I start from this picture, which all you know, that is the kilonova. I showed this because we all agree that it was because of the multi-wavelength follow-up of the trigger that we learned really what was going on. Because at the beginning we had a signal from merging with binary into star and peculiar at that time short GRB. But then following up all wavelength, we learned that the GRB was not peculiar, was just slightly off axis, which the jet has a structure that there was everything, the heavy element formation that we know the distance and so on. So the key there was follow-up. But for the source we are talking now, what is more important, I'm not talking about follow-up for two reasons. First, the instrument will come in sometimes, so we will have time to talk about that. But also in few cases, we will not have nothing after the, okay. We will nothing occur after the merging, so after the gravitational wave signal. So we have to, the multi-messenger will occur before. Let's see. Why is it not moving? Okay, showing this picture again, which has been shown several times, because we know that there is a sequence of, in the frequency range, we have a sequence of mass merger. So the less massive binaries merge here, the more massive binary compact object merge here, but the wide dwarf binary merge here, which are low mass, 0.6, let's say 0.6 in this picture. Why that occur? Because they have a much larger radius, several thousand kilometers rather than 10 kilometers. So they occur there because just in the Decihertz range, so they are very important sources. The list of sources that we can make are these. Some of these will be discussed, have been discussed before, some will be discussed later. I will focus on closed binary wide dwarf, which so far have been touched but not much discussed. So I showed this plot, which we made a couple of years ago. So the sensitivity curve have to be updated. Don't look that, just look to the frequency. These are known detectable GV sources. So sources that we know the signal today, and that in principle can be detected provided we get enough sensitivity. And among these sources, most are double wide dwarf. There are, this is very interesting, ultra compact X-ray binary that Alexei just told us. And there are some other objects like these things, that it is a wide dwarf plus a main sequence stars, which, however, I mean, these sources, if you could wait for a million years in some cases, will move into higher frequencies. And while these wide dwarf main sequence stars, not, because they will be destroyed before getting in this regime. But this is interesting because this is an alternative for type 1a supernova explosion. So the sources here comes from random discovery in the many years in the past, but today also because of pointed dedicated survey. I will spend some time on this. And I will start from historically from this SPI survey, which was a search for possible candidate progenitor of type 1a supernova. So the people were searching for wide dwarf, high mass, close, that in principle can produce the supernova 1A explosion. And as you can see, they are at here. No one is within the Decihertz band, but the other, so there were other surveys contributing to this, and I will go there. Yeah, I will get to that. Well, it's not a selection, it's just that they spend much less time there. So there are much less systems. Let's see. Black. Okay. So I have to, Alexei already give some of the term in this game, but I need to tell you where this double degenerate system come from. This double white dwarf system. It is a very complicated, so you need to have the evolution of low mass star, because if they are higher mass star, they will explode a supernova, produce a neutron star. They are not what we are talking now. They need to be lower mass, less than 8 solar masses, produce a white dwarf at the end of their life. And they need, for our case, they need to be in binary system. And if you want to detect that as a gravitational wave, must be closed binary system. So there must be, their period must be short. So what happened to this system? It is a very complicated scenario where you have the two stars, one of the two evolve, the core burn all the hydrogen, you get the helium core, the envelope expand, and the matter, the expansion will cause a big envelope which include the companion, and this is called the common envelope. These things at this point, this gas does not rotate with the two stars and is just ejected. If it's not ejected, it can go, there can be a merging of the two stars. So nothing will, you will add two stars at the end, you will have one single. This is interesting. If I can have time, I will get to this. The common envelope will be, after it is ejected, you will be left with one white dwarf and the main sequence star. Up to here, there is not much to see, but starting from here, there are a lot of phenomena which can occur in closed system, because transfer of matter occurs from the main sequence stars to the white dwarf, and if this transfer is high enough, there can be an explosion as a supernova. If not, the secondary will evolve. There will be a second episode where there will be a common envelope. So again, the stars will become very large. And depending on the mass of the two stars, the efficiency of these things, you can have different tracks. Along all of these points, you will have phenomena occurring that you can see in the sky: cataclysmic variable, super soft X-ray sources, stranging of AM Canyon Veraticorum, which are stars where the secondary is now helium, and so the transfer is not hydrogen, but it's helium. And in many different places, you see it's written SNA. We do not know if this actually occur. They may occur. So we don't know which one dominate, which one is going on, so on. The picture of the system after the first common envelope, when you have the white dwarf plus the main sequence star, looks like very similar to the one of the ultra compact. So you have a normal star in this case, which fills the Robes-Schlobe, transfer masses now not to the neutron star, but to the white dwarf, which is the primary, the most evolved star. This occurs through a accretion disk, and all these things can cause very different phenomena. It depends also from the mass accretion rate, if it is high, if it is moderate, if it is low. Different kind of sources are observed in the sky. Strong magnetic field can also get a very important effect, because in that case, the accretion disk may not even create, but transfer can go through the field, the magnetic field line. There are alternatives, as I said. One is when the secondary is instead of being a main sequence star, is a low mass helium star, which is not getting enough mass to be fully degenerate. So we'll continue to transfer mass to the white dwarf. Or the transfer can occur where the first star is has become already a red giant, because it was possibly more distance, and you have another phenomenon, which is the so-called symbiotic. So let's go to the sources that we get. So as I told you, 20 years ago, Napivosky started a search. You want to find the double degenerate system, so system of two white dwarfs with masses above 1.4, the sum of the two, which could be the progenitor of type 1a. He searched, and it was a very expensive search, because it was selecting a sample of a candidate, taking spectra of this thing, need a big telescope, high resolution spectra, then wait, take a second spectrum, measure possible variation on the line. And in 20 years, he found around 46 double white dwarf, known as a mass, total mass above the, so that's the problem. You are searching for supernova double degenerate, and there are known in the galaxy at the moment. This search by construction was pointed to high mass white dwarf, but there are lots of low mass white dwarf. And so people will say, let's look to white dwarf of low mass, not because they are progenitor of supernova, but because they are interesting potential gravitational wave sources. And this search, for instance, was searching for a low white dwarf with mass less than 0.3, again, an expensive kind of search, and they found 100 white dwarf. A big change in this field came from Gaia, because Gaia, giving the distance of all the stars in the galaxy, can give us a powerful tool to select white dwarf. Because it is a color magnitude diagram of near the 100 parsec produced by Gaia. You see, measure 200,000 stars. Among these, there are 12,000 white dwarf. Here they are. And they could even distinguish binary from single. And the conclusion was that in 100 parsec, the binary white dwarf are about 1%. These yellow things here are, in many cases, the merger of two white dwarfs, which already occurred. And they are a significant fraction, 10 to 15%. Another way to search for a binary white dwarf, even at larger distances, in this case up to 170, again using Gaia, is to look to the residual, the astrometric solution. Where if you measure the same star many times, you have a residual noise. If this noise is too large, it may be because the star is not a single, but two stars, and so they slightly moving around the centroid. By this technique, Valerie found a number of, you see here, of these things which show a wobble in the astrometric solution, and they found a fraction of about 7% of white dwarf. Sorry. Okay. I lost the one slide, but just I will tell you what was there. There were other ways that you can search now effectively by binary white dwarf, which is by using the new survey, like ZTF, that will allow you to monitor the photometric evolution during a long period, and you can see variation in the light curve, which are typical of binary. And by this method, you can find many of the binary which I show in the first plot. So many of the no binary, which are also shown in this plot by Valerie, which was shown just before by Alexei, where these green stars are the non-binary in our galaxy, including those found by Gaia, by ZTF, and by chance in the field. The much larger number of points here are instead a simulated population of binary, which come from models of binary population synthesis, which need to assume a star formation is in the galaxy, a formation scenario. And so by including all these things inside, you have the predicted population of binary, which is, there are predicted quite a big number in the galaxy. There are 30 million double white dwarf. That, of course, most of them will not be detectable, will make a background. The Coral made the estimate that 60,000 will be detected by LISA. And you see there are a few points up here, which has of the order of 100 or so, which will be at frequency above 10 to the minus 2 Hertz. So now comes to the issue of supernovae 1As. We know that this is a recent Hubble diagram of type 1A supernovae, which span quite a lot of quite a wide range redshift, and of course we know that what it is always says, type 1A are perfect standard candle, and with that we found dark energy and these things now the Hubble tension. And why is that? Is that because they all explode at 1.4 solar masses, the Chandrasekhar mass. They are white dwarf that explode at this mass. I like to see this other way to this other view to type 1A, which is here you have the rate of decline of the light curve against the absolute magnitude. And you see that the absolute magnitude actually span 6 magnitudes. So why they are not standard candle really? What is used today in cosmology is basically this line here, which is a correlation between the two parameters. But you see that there are many other possibly rarer, not possibly, rarer classes of objects, which are there, and so why they should be all coming from the same scenario. Anyway, starting from the consideration that we need to have a double white dwarf massive to pray, there were the two main possibilities. The so-called single degenerate, so the explosion occurs after the first common envelope because of transfer of mass on the white dwarf, or it occurs when the two white dwarfs merge. This is where the two possibilities. The fact that Napivosky didn't find any system with the right mass was in favor of the single degenerate scenario. But I must say that nowadays, if you look to literature, most people believe that this path is the one we should follow. One of the reasons is that they use a variation of this, which is a measure of the evolution of the rate of the supernovae as a function of redshift. Okay, if you look to this plot, different scenario produce different line. However, you can easily see that the difference between different scenarios are mainly at high redshift where the error bar are huge. So I'm not sure that this is a convincing argument. So let's go to to my point. You know, the problem is that if you want to look to this system, in principle, you would like to see to the merging of the two white dwarfs in the Decihertz regime and then possibly to a supernova. First of all, what are our chances to observe one of these events? If you look to the galaxy, the rate is something like 1 every 2 centuries, so not very high. So I would look to the other side of the to have a constraint, and I take this approach. If we know the merging time of you take the white dwarf, take that they are merging because of gravitational wave emission, how much time they will take? Starting from a period of 1 hour, they will take 10 to million years. Starting for 200 seconds, they would still take 10 to the 4 years. If we have the rate of 2 per century, and how many events we should have in each of these period being, how many events do you need to have to produce the supernova rate which you observe of 2 per century? These are the numbers. So we have 100,000 less than 1 hour, less than 1 hour, sorry, 20,000 less than 2,000 seconds, and 50 less than 200 seconds. As I say, these are the merging that produce a type 1a supernova, but we have also merging for white dwarf of lower mass. We get some idea what is the mass distribution white dwarf, and if we include the merging of event less than the Chandrasekhar, which some will make less than the Chandrasekhar, this is the number of white dwarf system that we expect to have in this regime based on the supernova rate which you observe, that need to have to produce the supernova rate. If we do not find in the galaxy this system, the double degenerate scenario cannot work. So, what if there are not enough double white dwarf massive? Well, people is speculating about the possibility that even less massive, if the sum of the two systems is less than the Chandrasekhar mass, you can still have an explosion in particular configuration because of the ignition of helium on the surface of the star, which compress the less massive core and still produce an explosion. These are called sub-Chandrasekhar. And what if we do not see a supernova after a merger? As I was saying before, well, this may not be conclusive because the delay from the peak of the GG emission to the supernova explosion is unclear. It can range from 10 to the 4 years to a few seconds in extreme case. These things will occur if the ignition is triggered by the helium. So it's somewhat connected to the sub-Chandrasekhar scenario. So you need to have the ignition of the helium on the top of the white dwarf that trigger the explosion, and at the moment is not the favorite channel. So it is considered for a fraction, a small fraction of type 1a supernova. So I would not bet that you have the trigger, sorry, you have the merging and you will see the supernova. I was mentioning, are we going to see something from other phases along the chain that go from binary evolution? Well, there was this recent paper just published that shows that when you had the first common envelope, and in case the envelope is not ejected, but you have a merger, the merging of the white dwarf plus the red giant core produces a signal that you see is in the Decihertz regime. It is not huge, it is of the order 1 kilo. You see this is the signal at distance 1 kiloparsec, but is an event which can occur possibly with some frequency Do we have evidence of these kinds of merging, not from gravitational waves, in the galaxy? There are these interesting case of this 1309 Scorpio, where you have a system which shows of two stars, one is one and the other three solar masses, and they was seen to lose angular momentum, so the period was decreasing for quite some times. It was this phase here, and then you had the burst. And there were, after this, were found a number of events like this in other galaxies. Altogether, you come to a galactic merger rate of something like 0.03 to 0.5 per year, which some of these may look like the things that we have seen before. What about core collapse supernovae? For core collapse supernovae, there was the recent paper by Vartanian, which shows that you have this waveform to expect. It's very complex. This is a very interesting paper showing a number of different mass progenitor. And the thing is interesting for us here is that the signal is very rich, but the part which is on this side is dominated by the neutrino convection, and which dominate from sub-Hertz to several 10 of Hertz. So you see the signal here. This is for a galactic supernova at 10 kiloparsec. I don't go through this because Piran yesterday's talk of jet. When you have the core collapse of a supernova, you have that signal that we have just seen, but in some case, we may also have additional GV signal if a jet will occur. I don't go through this, but I go something on the statistics. How many events we should expect to see? We know that the rate in the galaxy is something like of the order of 2 per century. Well, where are all these supernovae? I did this plot over 20 years ago, and it was a distribution of the known supernovae in our galaxy historically. So you see that they are confined in a radius, in a distance of 1 kiloparsec, and in a sector, in a closed section. Why they are not in the other side? Because of extinction. And we may remember, sorry, that the two most recent supernova, which were the 1604, the Cappellaro one, and the 1574, which is the Tycho event, they were 1572 here. They were type 1a, not core collapse. We have a real core collapse supernova, which is the remnant of Cascade. This was not seen by eye, but we have the remnant. There is the pulsar, and interestingly, we have the spectrum of the supernova. Okay, taken because of the light echo on a circumstellar cloud, so we know it was a type 2. And this is also interesting because it's the most recent remnants in the galaxy, which is we think is about slightly over 100 years old, and the use is at 8.5 kiloparsec, and they suffer 15 magnitude of extinction. Let me skip this. So, if there is so large extinction for most of these supernova, the conclusion is the next is true. Finding galactic supernova is, we need quite some luck. But the next galactic supernova will likely be discovered by neutrino or GV detector because they will not be that visible in optical. I also give this number, which shows the which more relevant to your questions, even is a somewhat larger distance. With in 10 megaparsec and in 10 years, how many supernovae will be observed? 13 core collapses and 9 type 1a. This is just to to have an idea of many events will occur. 10 megaparsec is not that close, but it's giving a reference. Last couple of slides. I don't go through the many instruments, we can produce follow-up observation, pre-discovery, and so on. But there are three parts of this game. Study the astrophysical scenario, knowing what is there. Search for counterparts of the gravitational wave events when something is found, and in case follow up if there is. And you see there are more or less instruments for all these different paths and all different wavelengths and so on. There is one niche where we may need to do better, which is in the full sky coverage at moderate magnitude. And why that would be interesting. I show, to convince you, looks to this. This is the light curve of two collapsed supernovae observed by chance by the Kepler mission. That was, Kepler is a satellite looking for planets, exoplanet by transit. So they have many observations. Every 30 minutes, there is one observation. So they could catch the rise of the supernova. You see here, this green line here is the breakout of the collapse at the edge of the star. With this, you can have a very accurate timing of the explosion, which you can inject back in your gravitational wave signal to search for something. You need to remember that there is a delay from the collapse to the breakout, which is the time that the shock take to traverse the stars is about several hours. So the precision will not be seconds, but is still something interesting. The other point are, if you want to look to the short GRB after the gravitational wave event, we need to be there very soon, in the optical, let's say. We need to be there very soon and look to the wide area, 1,000 degrees. And at the moment, and we need to go to fairly faint magnitude, let's say, between 18, 20, something like this. We don't have instruments for these things at the moment. And so I show this just because it's my director, which is Roberto Ragazzoni, which is proposing these things, is an instrument which can accomplish these things. It is a sphere of glass, empty sphere, filled with some special liquid, which will be able to observe 20,000 square degrees with 1 arc second. 20,000 degrees means all the sky you can see from one place. And you see here the design. The problem here is that you need to have 4,000 CCD cameras to fill in, they are this one, to fill in the focal plane, let's say. And but the objects can be a size of a meter. Okay, I can allow to address to have a full view of the sky and to have a preview continuously, even if we are not able to fill the focal plane, but we say cover a fraction of that, say 2,000 degrees, and then we can point to some direction moving the CCD array. We can have a view of the full area of a gravitational wave signal just a few seconds after the trigger. And I will stop here.
Thank you very much. Are there any questions?
Thank you. So your explanation for the lack of galactic supernovae is extinction, right? So, but we have been having neutrino detectors in the last 3 decades. So
yeah, we are close to having a problem. We are close to that. You know, when I started this business, the The expected rate, which was 1 every 20 years, we had to give up to that. Now we are back to 1 to 50. 1 every 50 years is probably still optimistic, but we are working with small number statistics. So if you take, there is still a significant possibility where you're just in a minimum. I always am surprised that Cappellaro and Tycho in 30 years, they were observing 2 type 1a. So we need to keep that. There are periods fortunate and unfortunate. We had 87a, which is not galactic, but almost. And if you think we had that, well, when the neutrino experiment were working, not longer working. So if you count 87a as galactic, we are there. And adding the mass of the Magellanic Cloud will not change the expected rate that much.
Yeah, well, thank you so much. It's a very interesting, broad, big picture that is emerging, right? So I had a question about the future. So I mean, it's of course very hard to project, but because LGWA will probably, hopefully, fly in the mid-2030s, right? So I mean, probably the observations will make some systems very well studied, and some new questions will emerge. So maybe you could speculate how the landscape will change. What are going to be most interesting systems to study in the early 2030s?
What I expect is we will have many more identified sources for known sources of gravitational wave. That's, I think, will be very important. Even if for calibration of LWGA, you will have sources you can choose whenever you want to know the structure of the moon and so on. For the type 1a, one would say, well, in 10 years, we will have a solution. I'm not sure. With 30 years, we are looking to that. And we have this main problem, let's say, of the massive black hole found by LIGO Virgo, which we are not really sure where they are coming from a stellar evolution point of view. So I hope that we are, from our side, multi-mission, we are finding a way to constrain where these sources are coming from. And so they are expiring to us to search for something, that's what they say. I think the other important things is which still we have to work a lot is these things of the intermediate massive black hole. We don't have that. No, we don't have basically evidence from electromagnetic, possibly something. We should be able, not even for the binary, but even for the single, finding out possibilities or place, location. I have a statistic on that because at the moment they are very, very uncertain.
Thank you so much.
Are there any other questions? Not, then let's, yes, there we have.
Hello. Yeah, so I have a question about the a common envelope merger. So you mentioned a common envelope can drive the merger, and that will be detectable in Decihertz. But what if there's a scenario where the common envelope gets ejected and there's a compact binary merger that is detected in the ground-based detector band? So can you have a scenario where the multi-band observation can happen? And if yes, can you learn something new?
The merging will occur at much higher, lower frequency, will not come to the ground-based detector. So the merger, this is a merger of, say, a white dwarf plus the nucleus of a red giant. The frequency will be similar to that of a white dwarf merger. So at around 10 10 to the minus 1, 10 to the minus 2 hertz. So it will not go higher frequency. That's if I got your question. I'm not sure.
So if the core of these binaries are like neutron stars instead of white dwarf mergers, they can go, or they can be detectable in ground-based detectors as well, right? Is that correct?
Neutron star white dwarf? Sorry, I didn't hear very well.
So if the core of this common envelope, the common envelope evolution,
Yeah.
one of the cores is, let's say, neutron star instead of a white dwarf.
Yeah, then we go back. That will look like the case of the ultra compact some respect. It will be the merging of a white dwarf with a neutron star.
So even that kind of merger won't reach to the frequencies which will be.
Alex, I show that that's go to less than 1 hertz.
Okay.
Just maybe also quickly say that maybe, I mean, the mergers of, main sequence stars with the giant are frequent, but neutron stars with the giant are probably less frequent because neutron stars are more rare objects. So, I mean, then they have to wait for much longer to wait for that to happen.
Add a little bit. Yeah, it is probably still possible to perturb the neutron star quasi-normal modes, by falling sufficient amount of matter. You can correct me, right? So in principle, it is possible still to see very high frequency GW signal if the core is the neutron star. And if you put in sufficient amount of matter, it's quite possible. Excite G modes and F modes and everything.
Questions? Okay, if not, then let's thank Enrico again.